So a reaction that is in equilibrium actually does not go to 100% completion. So at the end of the hour, at the end of the day, at the end of the month, the reaction will still have some reactants left over. Now, how much? Will it be more reactants than products? Will it be more products than reactants? Are there equal amounts of products and reactants? In that case, the equilibrium constant is going to be 1. So this equilibrium is typified by arrows that go back and forth. So notice here the arrow is not unidirectional. So at the end of the reaction, at the end of the day, there will be some reactants left over as well as some products left over. They're going to settle, and they will settle according to the equation known as the law of mass action. Products over reactants. We do not add solids and we do not add liquids. So the reasoning behind that will be mentioned during lecture. The equilibrium constant is products over reactants. Again, no solids, no liquids. And for gases, we can just express them as concentrations, or we can express them as pressures. So some practice equilibrium problems here. So for part A here, we have a solid going to another solid and two gases. So we have expressions of the Kc or Kp. Now the reason why it can be Kc and Kp is because of gases. Gases can be expressed as a concentration, moles per liter, or as a pressure. So to solve for this problem, we'll just look at part A here. The equilibrium. So if I'm going to do just simply Kc, it's going to be the concentration of CO2 times the concentration of H2O. Okay, so that is C, which implies concentration. We can also do Kp, which is the pressure of CO2 times the pressure of H2O. Notice I didn't add any of the solids in there because solids and liquids simply just do not go into the expression. And there is a formula that relates Kp and Kc. P stands for pressure, C stands for concentration. You're going to use this only when you have gases. And the equation is this. Basically, Kp is equal to Kc times the gas constant R times temperature in Kelvin. The RT product is raised to the power of delta N, the change in the number of moles. So let's look at delta N for this problem here. We have 2 moles, even though it's a solid. We have 1 mole in the product side, 2 moles, 1 plus 1 is 2, and another 1 mole is 3. So 1 mole, 1 mole, 1 mole is 3. 3 minus 2 is 1, so the delta N for this reaction. Products minus reactants, change in is going to be 1. R is our gas constant here, which is 0.0821 liters atmosphere per mole Kelvin. And obviously your temperature has to be in Kelvin. So we can actually, if given Kc, we can switch it up and find Kp. We can find Kc if we know Kp. So there's many ways you can actually solve this problem. One way, and this is one way, we can sort of put our Kp term, we can put our Kc term into this equation for Kp. Okay, times RT. They don't really give us a temperature, so we'll just go with what they gave us, times T, and then the delta N, as we explained before, is going to be 1. So there's many ways you can solve these equilibrium problems. Same thing with part B in this problem. Again, we have 2 moles of the gas, so you got to remember the law of mass action here for part B. It's products over reactants, but we got 2 moles here. So actually it's going to be Kc is going to equal SO2, and we have to square it. So this is important. A lot of people miss this. We have to square it because there's 2 moles. That's the equation that is the law of mass action. This is what the equation tells us. It's squared. Why do I square it? Because we have 2 moles here. Okay. We can also do a Kp, which is going to be the pressure of SO2. We can square that times the pressure of O2 gas. Okay? So we can do the exact same thing here, and realizing that Kp is equal to Kc times RT, all of that raised to the delta N. This is one way we can solve this problem. We can put everything in terms of Kp, which would be the concentration of SO2. Don't forget to square now. Concentration of O2. R is 0.0 821 liters per mole Kelvin times T. They don't give us a temperature here, but it has to be in Kelvin. And what is delta T, the change in the number of moles? So we have 2 moles here, reactant side. Remember, it's products minus reactants. So 2 plus 2 is 4. 4 plus 1 is 5. So 5 minus 2 is going to be 3. So we have to cube this. So that would be an expression, one of the expressions for the equilibrium constant in terms of pressure. So if you're given the concentrations, you can get Kp. If you're given the pressure, you can get Kc by manipulating this equation here. So basically with gases, you can go back and forth between Kc and Kp.